It is August 1st, 7:55 a.m. Lecture 12. There we go. Lecture 12, where we are now. And this will go over several chapters, more chapters than any previous lecture in this series so far, from chapter 18 to chapter 16, just because, well, it covers, what's funny is it doesn't cover that much time, but it covers a lot of content. So it's going to be roughly about 230 years, from 1770 onward. And this will basically be it. Some chapters have covered like the expanse of thousands of years, but that just goes to show exactly how fast mathematics and the West as a whole, how fast they developed after unification under the same metaphysical principles, Christianity, under the Catholic Church, the stability of that after the fall of the Roman Empire, which didn't happen until, well, we've been over this, so I'm not going to harp on that. But let's talk about which chapter this is in Boyer. And it is chapter 18, which is on pre and post revolutionary France. Revolution. Sometimes. Okay. France. Let me just check to see if that's kosher. Looks good to me. Okay. So the time period we're going to be looking at least for this chapter, is circa 1770 to 1830. Now this is going to be interesting, horrifying, all that sort of stuff. Enlightening, but it's going to cover interesting figures like D'Alembert, Monge, Lagrange, Laplace, Legendre, Carnot, Condorcet. And basically what we're going to look at here is mathematics in France became more than inquiry. It became instrument of governmental thought and expansion. We saw this whenever we had those debates in between Leibniz and Newton, this sort of idea of mathematics becoming a symbol of prestige in the course of empire. And we see it taking place more explicitly here after the age of Euler and turning back to France. And the collapse of the monarchy and the ascent of revolutionary reason doesn't diminish mathematical power, they reforge it. Education is going to be weaponized in this period. Geometry instructed artillery, number governed the meter, mathematicians became architects of state, theorists of structure, and voices of reform, whether for good or for ill. We'll discuss that. This was not a return to classical purity, nor an abandonment of abstraction. It was the forging of rigorous modernity under revolutionary stress, where pedagogy, policy, and principle converged. So let's paint a picture of what exactly Europe looks like here. Just capture something towards the middle, that being, of course, I say of course, but let's look at 1812. 1812 in Europe. I know as an American, 1812 is, the war with Britain, but they were focused on a much bigger problem here on the European continent. So we'll draw sort of a terrible drawing of Britain, you know, that sort of thing on there. And we'll let's draw Cornwall properly. Okay. And go ahead and draw the European continent as best we can, which isn't that good, but it's fine. It'll be fine. Okay. And something like that. Onward. Basically, the thing to realize here is that in 1812, France pretty much governs or has favorable alliances with everything over here, everything on the European continent. Now, this is before they go into Russia. This is before Napoleon goes into Russia. And absolutely, well, except for, okay, let me caveat that they have favorable alliances, aka, well, rather domineering alliances with everybody on the European continent, save for in the Balkans area around there in Greece, because the Ottoman Empire rules over that. So, big scary Russia up here. This is before the push into Russia. So, that's the sort of civilization that we're looking at right now. Now, let's go ahead and look at some faces of the era. Some of the names I mentioned earlier. Among them was Jean Leron d'Alembert, who lived from 1717 to 1783. He was a philosopher, an encyclopedist, and an architect of analytic rigor. He wrote much of the Encyclopedia, including its mathematical and scientific content. He opposed the use of infinitesimals on metaphysical grounds, favored a proto-limit approach rooted in clarity and logic. So he was anti-infinitesimal, proto-limit. Via clarity and logic. He derived the wave equation for vibrating strings and proposed the Cauchy-Riemann equations in early form. He believed that the calculus should be founded on limits, not on infinitely small quantities. We noted that with the we can see that with the anti-infinitesimal perspective here. He is said to have stated a quantity is either something or nothing. So it cannot be both. There is no in between. Ergo, has to be an actual thing, a real thing. Fair point. Wouldn't like non-standard analysis. But anyway, his principle is that differentiation is the limit of finite differences. It's an early articulation of derivatives as process. All right. I might just write on a board like this from now on. Next thing. Etienne Bezout. French is hard, man. Okay. Who lived from 1730 to 1783. 1783. Goodness. Okay. He was an algebraist and educator. He authored military mathematics textbooks influential at institutions like Mézières. So we can see that sort of interplay of French government and power with math more directly here. Something like a kind of proto-military industrial complex, sort of what we saw with Archimedes in Syracuse, but this is way more formally backed than just Archimedes out there doing his stuff. So, yes, military textbooks, military mathematics, textbooks. Okay. He developed elimination theory using determinants, now bearing his name in the Bezoutian and Bezout's theorem. We are so privileged as English speakers. Well, mainly English speakers. We don't have to deal with any of these tildes or anything like that. Anyhow, he was the first to systematically treat the inspection of algebraic curves by degree. His Cours de Mathématiques was widely used in both France and the early United States. So the United States is starting to come to play here. Their revolution, of course, will influence the way more bloodied and less, I guess, axiomatically rooted French Revolution. I'll just say text for now. We'll talk about it. Right. He has a very, very long name, so we'll just call him Marquis de Condorcet. I suppose. 1743 to 1794. He was a philosopher, an advocate of human progress generally, mathematician of probability, and social welfare. Just in general, not like programs or anything like that. Wasn't really a thing too much. I mean, it kind of was. Rome gave their citizens like free bread and stuff, so I guess it's kind of. But okay, free bread. So he wrote on integrals, integral calculus, education, statistics, and political decision making. Education. Right. What else did he do? Well, he proposed one of the first formal models of voting theory. The Condor. I guess I better kind of decide what sort of C that is in his name. We'll just go with Ket because that's easier to say. The Condor-Ket method. First model of voting theory. This was, of course, the Condor-Ket method. He composed the visionary sketch for a historical picture of the progress of the human mind while in hiding during the Revolution. So we see that sort of humanitarian aspect to him coming back. And he died in prison under unclear circumstances. But, you know, you can kind of figure what that means. Yeah, like, you know, Putin and the leader of the Wagner group, you know, it's like, well, the plane crashed. So, proceed. Joseph Louis Lagrange. From 1736 to 1813. He was the author of the Mécanique Analytique, which sought to rebuild calculus purely on algebraic grounds. Eliminated geometric intuition and infinitesimals in favor of derived functions. Some might say that this is really where the beauty of the thing starts to be destroyed, which is, you know, a valid claim. If you look at like things like tensor calculus, those things are way more beautiful, but it's like, it kind of has to, if you look at mathematical history in full, it's kind of hard to argue that we would have progressed as fast as we did if we wouldn't have approach things in this way, like algebratizing, I guess you could say. Everything and anything we can get a hold of. We'll look more into that. Yeah, no geometric intuition that's stripped of the forefront or infinitesimals. And this was done in favor of derived functions. Function theory. He invented calculus of variations. And I say that kind of flippantly here because, you know, we've been going through all of these developments, but it's a pretty big deal. Calculus of variations. I catch myself saying that a lot whenever we're talking about mathematical history. This is a big deal, that's a big deal. Well, it's kind of all a big deal if you like, you know, this sort of stuff and, you know, you see the value in it. But let's look at this more closely because it's not just that. He also contributes to early group theory, number theory, and algebraic solvability. There's also this method that he comes up with. Let me just go over here, which is Lagrange multipliers. Those are also a big deal. And he clarified polynomial permutation theory. He's really an example of bridging Enlightenment elegance with post-revolutionary rigor. So he's not exactly in the way of Euler, where he just sort of builds these things and then speaks about them intuitively. The early underpinnings for true mathematical rigor, and at least as we see it in modern day, is sort of set here. Okay. First, let me see if that's... Yeah. Gaspard Monge, from 1746 to 1818. He is the father of descriptive geometry, founder of the École Polytechnique, Shirley's big institutions in France. Educational institutions in France. Okay. He elevated geometry to national service. Perspective, shadow, topography, engineering, it all falls under that noble goal of national service, depending on whether or not you see the nation in question as noble. But I mean, I guess it's kind of not inherently bad. Okay, so topography and engineering. He taught first systematic courses in solid and differential geometry. He authored a work called The Geometry, Descriptive and Advanced Analytic Geometry in 3 Dimensions. 3D, man. It's totally cool. This is the early 2000s, and it's like, it's pretty epic. It's so neat. I mean, 3D is so good. Geometry. He helped redefine the relationship between geometric representation and analytic method. Which are going to be two emergent, two of the three, well, yeah, I guess two of the three big mathematical branches that will survive in the modern day. Geometry and analysis. You could sort of argue that like it's not geometry anymore, it's topology, but it's kind of, I don't want to say potato, but it's kind of, because those are different things, so we'll just keep it at that. Right. Now, on to the next one, which is he's very important for France. I mean, all of these guys are very important for France, but this guy in particular, Carnot, big government guy. Lazare Carnot, 1753, 1823. He was a military organizer. So you know this guy is going to pop up in the history books. Military organizer, a metaphysician, which basically just means he supports the idea of the infinitesimal two thoughts. One of them wasn't finished yet. He's a metaphysician of the infinitesimal, which means that he supports the idea of this infinitesimal existing despite outside of a prevailing physical phenomena with which you can observe, influencing the development of calculus. So it's an underpinning. The infinitesimal as an underpinning of calculus. His réflexions sur la métaphysique du calcul infinitesimal offered a principle of compensating errors as the foundation of calculus. So, error compensation. And we see this kind of with, I know in PDEs, in partial differential equations, sometimes you'll have like an error function. And that's kind of what it is, where it's like you can't have like a closed form solution of a thing, and because it's too complicated, and so you add on like an error function. But it's kind of like that, but not exactly. But anyways, error compensation in calculus. That's the takeaway. What else? And I should note that he saw that as foundational. Like that's a thing you've got to have. It's kind of like not really the way we play it. We kind of play it in a way that it's like we'll teach it in the notation of Leibniz with the rigor of Newton as best we can to people that are just studying it, which is fair. It would be something else to try and put all of that as just like a foundational thing. So it's probably for the best that we didn't include that too much. He extended Menelaus's and Heron's theorems, he proposed intrinsic coordinates including aberrancy. It's like an aberration. There we go. Aberrancy. Though that is not an adjective I use very often, I must say. Well, no, it's not an adjective. It's just not a word. It's just not a word. There's a more specific thing. Okay. Intrinsic coordinates, extension of Huron and Menelaus's theorems. So, he also introduced the idea of geometry of position and sought a unification of geometric theorems through algebraic correlation. So it's kind of like, it doesn't matter what sort of coordinate system we put it in. We know that one part in relation to another part will always be in this way, in that way. So, geometry of position. And he saw a unification of geometric theorems through algebraic correlation, which kind of goes back to that idea of like it doesn't really matter which coordinate system we put it in; it will always be such that in relation to these parts. Kind of goes back to what the Greeks were doing in a way, but the Greeks didn't really have like this level of formalism. So, but yeah, as I mentioned, this guy is really important to the history of France in general, not just the history of mathematics. He was a mathematician for one thing, a general, and a statesman. So this is definitely this is somebody who's going to be Napoleon's friend right here. Well, somebody who's akin to Napoleon at the very least, rather. And we'll see that. We'll see this sort of like anti-Napoleon versus pro-Napoleon split that happens here with some of the mathematicians. Because Napoleon's a big figure. He's a polarizing figure. That's what big figures are. People that do a lot of things are going to polarize a lot of people because they're doing a lot of things. So, and people have opinions about a lot of things. So, Pierre Simon Laplace, 1749 to 1827. He was the author of the Mécanique Céleste, which helped him to complete Newton's vision using analytic techniques. He developed the theory of probability. He developed it in what terms? Including Bayes' theorem. Bayesian statistics is everywhere. It's very important. Poisson distribution. We'll get to talking about Poisson here in a moment. He introduced the potential function. It's a different realm. Potential function. Of course, an equation bearing his name, Laplace's equation. And operator theory. So he was an advocate for determinism in mechanics and dismissed divine intervention as unnecessary in physical explanation. Which is really interesting because it's like, it's kind of like a deist perspective in a way. Calvinistic deist perspective. It's like no divine intervention because God's a clockwork maker. Also, the clock just keeps running on time. It's like which is a stance you can take. And so he takes it here. It's important to note that in this case, it's just for like mechanics. He's not saying like, well, we'll sort of leave away the philosophical quandaries on that for now. Just to say that he saw deterministic mechanics, which is true at a lot of levels. So deterministic mechanics and dismissed, not true in the full level, but and dismissed divine intervention as unnecessary physical explanation. So that's it. He merged astronomy, physics, and mathematics into one coherent analytic cosmos. He's kind of like Spinoza. It's kind of like smooth. I need to read more. This is his perspective on that. Okay. We have the last 4 names here coming up, and then we'll get to bigger things. But you know, if you don't like in particular any section of the lecture, this is going to be available on video format. You can just skip it if you like, but I have to actually be here and proceed through time regularly. You can pretty much just skip ahead. Okay. Adrien Marie Legendre, which is like the most French name that is ever Frenched other than Louis. But I mean, Louis is kind of, that's a Spanish thing too. So. 1833. Brought reader to geometry in his Elements de Géométrie. Which, by the way, I'm not like writing down the works and whatnot yet. And the reason for that is because, well, throughout this period, we're basically going to see the number of works skyrocketing. So me sitting here writing all the works and the explanations, it's kind of not going to work. Like the faces thing, the faces of the areas, like it kind of barely works because there's so many, right? But anyway, back to the point. Adrien Marie Legendre, from 1752 to 1833, a more rigorous geometry. Increased the rigor of geometry. He published a major work on elliptic integrals, Legendre polynomials, and beta gamma functions, which the last two are kind of number theoretical. Well, I mean it's all number theoretical if you're dealing with like. There we go, elliptic integrals. Legendre elliptic curves or so. Legendre polynomials and beta gamma functions. He was an early contributor to number theory here. Here we go. And one of those things, more specifically, which he developed in early number theory, was, well, let's just go through 3. Quadratic reciprocity, the Legendre symbol, and the distribution of primes, which became a thing which people are still very fascinated about because of that cryptographic element. Well, not just because of the cryptographic element, but that's a big part of it. He helped standardize methods of geodesy and data analysis, so including the least squares estimation. So you kind of look at all of this stuff at just from the history of math, and then you can kind of understand why Napoleon was able to accomplish as much as he did with the logistical situation, the logistical advantage that France would really have from just this, like I mentioned earlier, this skyrocketing of the process in a way. The skyrocketing in the pace of mathematical development. So yeah, another thing about Legendre is he was a quiet reformer over across analysis and arithmetic. So it wasn't just geometry, right? So it was also across analysis, which makes sense. If you're gonna be increasing the rigor in one area, why not do it to two more? Okay. Now, Joseph Fourier, I think he's probably most famous for the Fourier series. Okay. He synthesized analysis and heat theory, so this intertwining with physics and mathematics is becoming more prominent. He introduced Fourier series, which allowed for the representation of arbitrary functions via trigonometric expansions. So, and there's some really beautiful depictions of this online. I know 3 Blue, 1 Brown has a very nice video on it, so that's something to look at. He expanded the definition of a function. Which would open the door to modern analysis. Analysis as we see it today. Some of the big names that he influenced here. Dirichlet. I've heard people pronounce it Dirichlet, but I'm going to go Dirichlet. And Sturm, and there's many others. But those ones in particular I'll mention because they come up a lot. His work formed the bridge from Enlightenment physics to functional analysis. It's just amazing to think that, like, a lot of these grad courses and stuff, it's like, it goes all the way back. It goes so far back than anyone would ever expect. There's this big argument which is like, oh, engineering's harder because we take the math stuff and then we apply it. But then it's like, you're using math that we had from like the 1700s and applying it. Which is, you know, still hard. It's just not a good argument for why your field is, well, why one would argue that your field is more, I guess, complex. Just due to the fact that tons and tons of theory upon theory on pure abstraction comes from layered mathematical development. So it's just, but that's a different point entirely. So, Enlightenment physics to functional analysis. That pretty much well covers it for Fourier just in general. Why did I put that there? Fourier's. Fourier. Yay. See? Okay. Okay. We still got a lot to cover, so we've got to speed this up. Oh no. Okay. Okay, all right. You know, I'm sitting in a chair. And when you're sitting in a chair, you really speed up on things. It's kind of, well, just talk to racers. It's like, yeah, of course. Go, speed racer. 1789 to 1857. Augustin Louis Cauchy, systematizer of calculus. Formalized definitions of limit, continuity, derivative, and convergence. Can you argue that this thing that converges is also Cauchy? It's like, no, I can't. No, but, yeah, so this demand for more and more rigorous and more specific explanations is going to be quite a theme here. Pioneered complex function theory. Complex function theory, as well as determinants, as well as integrals bearing his name, Cauchy integrals. Is that kosher or is that Cauchy? Okay. And uniform convergence. These big names make me write a lot. Okay. He authored textbooks that shaped rigorous analysis across Europe. He introduced criteria for convergence and methods for solving differential equations with existence theorems. It's funny how like all of undergraduate real analysis is taught within the anti-infinitesimal perspective. I guess you could say. I guess it's just a lot easier to continuity convergence. Criterion for convergence. And yeah. I don't even know if that can be seen. Yeah, that can be seen. That's jeez, that is ridiculous. Okay. Doesn't mean I should write down there, but what's up there is over here, which is basically just extension theorems, right? So. Yeah, and so he's a big part of this putting rigor into the bones of mathematics that way, where mathematics really becomes, I mean, it's always been rigorous to some extent, but to the level at which it has now become is very much laid here, and he had a big role to play in that. Well, all of these figures to some extent do, right? But let's just put a little bit of emphasis on Cauchy. Right. Onward and upward to Simeon Denis Poisson. A little bit of that French passion and things. Spanish have way more passion though. Or at least they used to. 17 shows a map of the Spanish Inquisition. That's diabolical. Okay. Okay. Physicist and mathematician. What? No way. A physicist and a mathematician? There's no way. Okay. Who brings the analytic heritage of Laplace with 19th century physics? Contributed to potential theory, probability, celestial mechanics, elasticity, electrostatics, on and on and on. Just keep on giving them accolades. Just keep on giving them accolades. Okay. Potential theory. Probability. Celestial mechanics. Celestial is such a nice word. Whenever I think of celestial, I think of those, what is it, Kid Icarus? Kid Icarus, whenever he's on, like, a spaceship. That game is wild. But, celestial mechanics, elasticity. What city is this? It's elasticity. Ha ha ha. Atrocity. Okay. electrostatics. He's known for a lot of things bearing his name. So in particular, like just put the word Poisson, well that's not a word, his name before, right? Poisson, and then it's like everything under the sun, right? No, but it's just Poisson integral, brackets, equation, ratio, get ratio, and distribution. And also Fabergé eggs. No, not really. So there's a lot of that going on, right? You know, like I'm gonna name this thing after me, and I'm gonna be known forever. And it's like Poisson was like, I'm gonna be known for all of it. But no, I shouldn't attribute ego where perhaps there is none, because I haven't done like a character or like psychological analysis on all of these individuals. Just a basic cursory glance. You know what I'm showing you here, a basic cursory glance as they relate to the history of mathematics. So that's so he's a big publisher. Like you know, we saw with Euler, tons of papers in the hundreds. He's up to around 400 publications. He was up to around 400 publications, which include influential treatises on mechanics and probability theory. So he's very important. Very important. We'll come up on a chapter on Guass, and Guass will be like, yes, of course I'm important. Again, probably shouldn't say. But oh well, sort of let it. Euler was very humble. Euler was a very humble mathematician. And so like in the face of that, it kind of makes it hard whenever you're looking at like mathematicians that even show like the slightest bit of ego to go like, oh, that guy's a prideful douchebag. But it is what it is. And you respect the intellectual achievements of that, and while you address the moral questions on the other side. Not to say that they should be entirely separate, but just throwing that out there. Okay. Now we turn to institutions and reforms. Yeah, as I mentioned earlier, we're not going to be having a section on mentioning the works and going after them because there's just too many. And we'll see later that would be a ridiculous, well, that would be just even more ridiculous than the part where I include like Faces of the Era, which is kind of something I feel like I'm more obligated to do. Let's see. Yeah, institutions and reforms. We'll just kind of like slot all of this stuff, all of these papers, these publications. I could have done journals. I don't know. It's complicated. For now, let's just do this. We'll just go over institutions and reforms. So, the Academy, the sciences, and Institute National. All of the kind of French pronunciation I only know through movies. Like Madagascar 3. Okay. So the Royal Academy of Sciences, which is France's leading mathematical institution throughout the 18th century, it gets shut down with the Revolution, right? You know, they're shutting down a lot of things in 1793. That was one of them. So in 1795, the Institut National des Sciences et des Arts was created to replace the former academies. So, you know, royal stuff gets shut down. And I guess, yeah. Revolutionary stuff in place. Now, in this institution, there were 3 classes really, and those were the physical and mathematical sciences, moral and political sciences, which, you know, a lot of people would argue is not a science, political science. Like, a lot of people in that study would say it's not exact, which, you know, is pretty funny, but depends on how we define the word science, right? But literature and the fine arts. So these are the 3 sections of this institution. No more, no less. Not 1, not 2, 4 won't do, but 3 will. So, Napoleon in 1792, he joined the Institute in 1789, which elevated its political and scientific prestige. And it was reorganized multiple times, but the Academy's mathematical activity was largely preserved under various names. Even to this day, it's kind of, you know, I shouldn't say kind of, but it's up there. It's up there. It should get put on a list. It should get put on a list. It's put on this list. Top 5. Get like a tier list going, right? Man, that would be something. Tier list of mathematicians. Yeah, you could make a tier list of mathematicians, and then you could. That's kind of mean. I don't know. That would be kind of mean. Okay, the committee on weights and measures. Also, like, I've noticed, like, people have many tier lists of mathematicians, but sometimes they take in, like, moral considerations, which makes sense, but I would say, like, a tier list on mathematicians insofar as their overall productive totals towards mathematical theory, I think would be the better way to do it. Because it's like you don't want to put like John Jones, right, on like a moral level, because then it's like, well, there's a lot of people better than John Jones in terms of that, but it's like, in terms of a fighter, John Jones is pretty high up there. But anyways, the Committee on Weights and Measures. Tasked with rationalization of measurement standards. The committee included Lagrange, Laplace, Monge, and Legendre. So those are big names. We've looked at all those names. So yeah, rationalization, which means like a more rigorous step by which we can understand these things. Everything follows a standard, we can measure it. It debated in this committee. Let me just put the names. And Legendre. So they debated the standardization via the pendulum versus terrestrial measurement. So you can measure everything by the Earth or, you know, on the precision of a pendulum. Ultimately, it defined the meter as 1/10,000,000th of the distance from the equator to the North Pole. So our definition of the meter comes from here. 10 millionth. I can't remember. What is that? 10 to the 7th? I'll just say that this is supposed to be 10 millionth. This is like, what if that changes by a hair, you know, with the deformation of the crust insofar as you can look at it. And through secondary to theoretical advances, this reform gave mathematics tangible administrative power. We'll see later, like Britain does this thing where they come up with the way that time is perceived with the Greenwich mean time, which is like, you know, still gets used today, and it's like the British Empire has control over time itself right now. It's a very interesting thing. It's just that it's so rigorous that, of course, everybody's going to take it and use it. This one I mentioned earlier, E equal A normal, 1794.